So here we are at lesson 8C, titled How Money Makes Money. Interest is the amount charged for temporarily using someone else's money. When you borrow money, you must pay back the amount you borrowed, which is called the principal, plus the interest that the loan has accrued. To the lender, the interest is income. In most cases, the interest is a percentage of the amount owed, which is called the interest rate. Again, whatever you're using, whether it's a glossary or flashcards or a Google Doc to keep a document of the words that we're talking about in class, you need to add these to that list. Question number 1, what's the purpose of interest and why do banks charge interest on loans and why do they pay interest on savings accounts? This is the perfect time to hit pause, answer question 1, look at the objectives, underline some information, and even looking at the paragraph that's just after the objectives. Do those things and we'll work through the rest together. So in question 1, looking at what is the purpose of interest and why do they charge interest on loans and pay it back on savings account, lending money is a service and the interest is the fee for that service. When banks lend money, they are providing the service, so they charge the interest. But when the customer puts money in a savings account, the bank can use that money to lend to others, so they pay interest for the right to do so. This lesson, you're going to understand the difference between simple and compound interest. And one thing you might even think about are simple fractures and compound fractures. One is simple and the other one has multiple parts. How interest relates to linear and exponential mathematical models. You'll be able to describe the difference between that simple and compound interest mentioned earlier in practical and in mathematical terms. You'll also be able to compare and contrast patterns in linear and exponential models. There are two types of interest that can be paid to an investor or charged to a borrower: simple and compound. With simple interest, the amount of the interest is constant throughout the period of the loan or the investment. Highlight, mark this, put yellow sticky notes, but the simple interest, the amount of the interest is constant. However, with compound interest, the interest is added to the balance in each investment period, which could be monthly, weekly, annually, and the percentage of that interest is calculated on the new balance in each investment period. So a whole lot more going on when you're talking about compound, where you keep adding back to the balance of the investment period and the percentage. A whole lot of stuff's going on with this compound interest. If you haven't already hit pause and complete question 2 and then come back and we'll do it together. But one thing to note as you're preparing for our next test together, this type of question is a great type of question to put on the test, where you're going to be looking at simple interest, and in just a minute we're going to be looking at compound interest. You're going to need to know how to calculate them distinctly, and one is simple and one is compound. Suppose you do invest $1,000 in a savings account that pays 2% simple interest, and it's per year. When computing simple interest, 2% of the initial balance of $1,000 is added to the account every year. So it's 2% of the initial balance is what gets added to the account every year. That's it. The amount of interest earned is the same each year. So they're asking us to complete this table, and I need to be careful. The initial deposit's not going to have any interest on it, but the initial balance is going to be $1,000. At the end of the first year, we're going to earn 2% of this initial investment. Put that in your calculator, do it by hand, but either way you go, if that money stays in the bank for the full year, you earn $20. Now this is probably okay so far, and the next part is where it starts going awry if we don't really see this part right here. And that's going awry right there. The amount of interest earned is the same each year. In this case, it's 2% of the initial balance. So I can go ahead and finish this part over here, because in a simple interest, I'm going to earn the same every year. So the second year, I've earned $20, so that means I'm now at a balance of $1,040. The end of my third year, the end of my fourth year, and the end of my fifth year. This completes the chart for simple interest. Part B says, calculate the common difference of the total balance between each year. Some of you might say, duh, right now. It's like, well, duh. We went up $20. We went up $20. I like writing on this side because it can tell us a whole lot of what's going on, because we don't always have this piece over here to tell us. But each year we went up $20. So the common difference, if we subtracted the two, is $20. And I've got plus up $20. Continuing on with question 2, part C says, suppose this process continued for 30 years. How much interest will have been earned and how much money would be in the account? Looking back at the chart, for our first year, we earned $20. So first year, we earned $20. The second year, we earned $20, but we already had another $20, so it was 2 years. Actually, it's a 40. That's what we went up. The third year, we also earned 10 years, $20. But if we look back at the chart, we actually went from 1,000 to 1,020 to 1,040 to 1,060. So a good pattern is to take our years and multiply it times that interest that we are earning. So for 30 years, at $20 each year, we can put the 20 down here and get us a 6. We would earn $600 in 30 years. The second question of how much money would be in the account, well, we started with 1,000 and we earned $600 over those 30 years. So our account would have $1,600. The question goes on to say, well, let's write an equation and then let's use our equation to really prove or show that it's going to be $1,600. And thinking about the looking at the chart, I'm not going to go back to it, but I have to go ahead and look at this like a graph. It really helps my brain to see the equation. And we've got year 1, year 2, year 3. So we have years, we have time again, and then we have our on the chart it said B for balance. So the 1,000, 1,020, 1,040, etc. With that thought in mind, this could be our X, this could be our Y, and our equation so far that we've been using is Y equals mx plus b. So we have our Y, we have an X, we need to know what the slope is. Well, the slope is the rate of change. How much are we going up each year? Well, each year we are going up $20. Now can we decide where we're starting? Well, the initial investment's where we're starting. So we can take, instead of Y, we can put B for the balance, M being $20 every year, so times the T, times the time, plus the fact that we started at $1,000. And we've got an equation. But it also says use the equation to calculate what's going on at the end of those 30 years. So My B equals 20T plus 1,000. So what's the balance going to be that's going up $20 a year for 30 years and then add it back to the initial investment? There's that 600. Here's that 1,000. And lo and behold, using a graph or just some math and our equation, we can come up with the $1,600. What kind of model is this simple interest and why? With us having that common rate of change where we go up $20 for every 1 year we leave this invested, with this slope, this is a linear equation. Oh wait, there's one more. Part F. So sketch a graph of the relationship between the total balance and the number of years, and then describe the shape of the graph. So I already kind of got it started over here, but it's really jammed up in the corner. So it would be nice if you made this larger, and then I'm going to show you some samples on the next slide. Here are a couple of nice looking graphs compared to my scratching just a while ago. But looking at this one, there's a nice title, Simple Interest on Investment, as I made that not readable. And then on the side, it talks about the balance, and that's not readable either. But there's a balance, and then you have the years since the initial deposit. And everything starting at 1,000, it's going up to 1,020, 1,040, 1,060. This is a great graph. The one beside it is starting at 0. Notice it's starting with $1,000 and the 0 years. And notice that they are the same information, but because of the difference in the y-axis, one looks like we're gaining a whole lot of money over here, and the other looks more gradual. Make sure you get a graph for this information. And if you haven't already done question 3, go ahead and look at it, and then catch up with me on this video. Now let's suppose that we have the same account, but this time the interest is compounded. We will assume that the compounding occurs annually. And compounding means that each year, you're going to add 2% of the previous year's balance to the account. And then the amount of interest earned changes each year. Again, in your notes, make huge notes about compounding, in that each year we're going to add an amount of interest to the previous year's balance, and this amount of interest earned is going to change each year. So part A on question 3 says, use this information to complete the table, round all dollar amounts to the nearest cent. So it starts very similar. We have an initial deposit of $1,000. We have an initial amount of interest, $20, where it's 2% of the $1,000. And so for the first year, we have earned $1,020. But the difference happens right here. We are no longer going to be looking at this number, and we're no longer going to be looking at this number. But yeah, after year 1, we have a balance of $1,000 and that $1,020. But to calculate interest that goes here, we're going to need to multiply this new amount times the 2%. That's a distinction for the compounding. So I've got 1,020 times 0.02, and I get that my interest the second year is $20.40. Now I add it back to my last, where I was last, that last year's balance, and I get that for my end of year 2, I'm at $1,040.40. So at this point, you might want to stop, think on this, calculate, manipulate, and then try, if you haven't already, try to get to year 3. Because to get to year 3, I don't care what was going on in year 1. I don't care about the interest in year 2. I care that my balance for the year before, year 3, was this $1,040.40, and I'm going to multiply it times the 0.02, and I get a new interest of $20 and, rounding to the nearest cent, 81 cents. So $20.81 I'm going to add to what I had the last year, $1,040.40, and I get a new balance of $1,061.21. This process continues, that if I'm looking for the interest for my 4th year, I don't care what I got any of these prior moments except for what I got as a balance in year 3. I will multiply it times 0.02 times 0.02, and my new interest is $21, and to the nearest cent is 22 cents. I will add it to the $1,061.21 to get a new balance of $1,082.43. Now, when you do this, you're not going to be crossing everything out like I am. I'm doing it to emphasize a point. All of these numbers will be showing, all of these numbers will be showing, but I'm trying to overemphasize that now, to be able to get the interest that goes right here, I go to this balance and multiply it times our 2%, so 1,082.43 times 0.02, and my new interest for year 5 is $21 and, rounded to the nearest cent, 65 cents. I will add $21.65 to $1,082.43 for the final balance in this scenario of $1,104.08. Remember, all of this, when you do this on homework or a test, is going to remain showing. I just wanted to emphasize where all the numbers are coming from. Part B asks, suppose we continue this for 30 years. Oh my gosh, we only made it to year 5. How would we determine how much money would be in the account? Will we have to continue yes, we would have to continue this process. And 7 and 8 and 9 and 10, surely there's a better way. Well, I'm glad you asked. That brings us to the next part of our lesson. If you haven't already tried parts C, D, E, and F, go ahead and try those now, and then come back and we'll work together on part C. To start the process of finding an equation, yes, we want to find an equation. Find the ratio of each total balance amount to the previous total balance amount, and the first one started for you. So the words that are missing are the total balance after 1 year. So the chart we just worked on, the total balance after 1 year was $1,020, and the total balance after 0 years was $1,000. So sticking this into the calculator, I have $1,020, and that wasn't correct, $1,020 divided by $1,000, and I get a number of 1 200ths. We are looking for a pattern, so we're going to keep looking on the next piece where it says total balance after 2 years and total balance after 1 year. So looking back at your chart, total balance after 2 years, well, I know this is 1 year, and total balance, let me go backwards, total balance after 2 years was $1,040.40. So I'm going to take these numbers and I'm going to plug in $1,040.40 and divide it by $1,020, and we get the same ratio. If we were to continue this for the rest of the chart that we created, we would find that there is a common ratio of 1 200ths. So part D says use your answer in part C and the fact that exponents represent repeated multiplication and work on that in order to construct an equation for this relationship. This is a really good time to hit pause where you are looking for the balance, and you're going to use the number 1,000 because that's the initial investment. You're going to use this 1.02, and you're going to use your time, your years, like after 1 year, 2 year, and 3 year. This is a really good time to play around here with an equation and then to test it. Do not go 1 year, 2 year, 3 year. Jump straight down to 5 years. And can you plug your information in with a 5 and come up with a number that is on our chart? Play around with that and then come back and let's talk some more. The equation that's going to work is when you take your initial investment and multiply it times this common ratio to the t power. With that in mind, use your equation to determine this amount of money after 30 years. Remember the smiley face up here? There's got to be a better way. Our balance for 30 years, where we don't have to do year 1, year 2, year 3, year 4, year 5, year 27, year 28, year 20, 30. All we got to do is come over here and say, what's our initial investment? It's $1,000. What is this common ratio? And we're going to talk more about that as the time progresses for us. And then put it to the year of 30. So in your calculator, you're going to need to become familiar with where your exponential key is. You're either going to have like a caret key or a y to the x key. There are multiple ways it can show up on your calculator, and you need to practice using your calculator. I'm going to encourage us to start back here because calculators are only going to do what you tell them to do. So I'm going to work on and telling it how to do stuff and make sure it follows order of operations, but you and your calculator can just straight punch it. But I'm going to start at 1.02. And then on my calculator, it has a button that looks like this, x to the y. So I hit 1.02, then x to the y, and telling it I want to go to the power of 30, and I hit equals. Then I'm going to come back and hit times 1,000 equals, and then I get this number. Round to the nearest cent. And so in 30 years, an initial investment of $1,000 at 2% interest will have grown to $1,811.36. This model is called exponential because it's growing. Oops, where do you think that name comes from? Because it's growing exponentially. It has an input variable that is in the exponent. So finishing up question 3, part G asks us to describe what compounding means from a practical perspective. What does it really mean when we calculate interest on the previous year's balance? And you could write something like interest is accruing on the original balance plus the interest that has already accrued. Part H asks us to sketch a graph and describe the shape of the graph. Here is a sample graph. It has a good title about compound interest, the balance on the account, and the years since the initial deposit. So part H asks you to sketch a graph and then describe the shape of the graph. And this one's different from our linear, that linear is going in a straight line, and this one's got a curve going to it. As we finish up this lesson, question 4 asks us to compare the table from question 2 to the table from question 3. One was from simple interest, the other is from compound. Describe the differences that you notice and state which account earns more money for the saver. Looking at part A, something you might could have written down is that for simple interest, the interest column is constant. For the compound interest table, the values in the interest column are increasing. As a result, the balance values in the compound interest table in years 2 to 5 are larger than those in the simple interest table. Finally, Part B, which model, the simple or the compound interest, results in a larger balance? And also, what does this suggest about the difference between exponential and linear? Something you might have written could be that compound interest results in a larger balance, suggesting that exponential models grow faster than linear models. This concludes our lesson 8C. Look at your syllabus to see if there are more lessons to do for this week. If not, you're finished with videos, but you do have homework to complete. I'll see you in another video very soon.